All right, so this is the first question we've received on exercise 8.4. So exercise 8.4 is going to be very similar to 8.3 in that we have multiple reactions taking place in an isothermal CSTR. So here we have A plus B goes to desired product, and then we have this parallel side reaction in which A plus B reacts to form an undesired product. We're given our two array expressions, one that's first order and concentration of A, second that's first order and concentration of B. We're given the initial concentration of A, so A is 10 molar, B is, so it's not 10 molar, it's 10 moles per gallon. So you can just take 10 moles per gallon to be your units of concentration. B is 12 moles per gallon, temperature is 350 Kelvin. Okay, and then, here in exercise 8.4 or 8.3, you had created a vector of tau values, and then you set up a for loop to loop over the values of tau in that vector and to solve for each particular case, right? And then collect the concentration of A, B, and C for all of those different tau values. Here, though, we're already given a value of tau, right? So we're told that the feed is that we have a 25-gallon CSTR, and that our inlet volumetric flow rate is 12.5 gallons per minute. So essentially, in this problem, you're given a value of tau, right? So you're solving for a specific value of tau, right? And so right off the bat, if I'm just thinking about the last problem, so we know the inlet concentration of A and B. We can assume that D and U, the inlet concentrations are 0. Everything in our rate expression is provided, right, since we know the temperature. We know tau, and so I could readily set up, a system of 4 equations with 4 unknowns and solve for the concentration of A, B, D, and U. Okay, and then, the problem just asks you for, essentially quantities at that specific tau value. So conversion of the limiting reagent. So that's our fractional conversion of the reagent that's present in the smallest amounts. In this case, it'll be A, since it's 1-to-1. And yeah, that's it. So it just wants the fractional conversion. So it'd be fractional conversion of A. And then we want the selectivity of D relative to U for that specific tau. Okay, so let's look at the specific code that was sent, and let's just see what we have. Okay, so we have this function titled reaction feed. Let me go back real quick. I know you want me to come with you. So reaction feed. Open up a new figure. So initial concentrations of A, B, D, and U. So we have 0 for all of those. Okay, so 1, it doesn't quite seem a little right. So let's come back to this in a second. So we have R and T, right? T was 350 Kelvin. Okay, that's good. You're creating a vector of taus, which is fine. We can come back to that specific case. And then you're going to solve for A, B, D, and U, right? So basically, it looks like we're just modifying our code from the last problems, which is good. Looking at our stoichiometric coefficients, so reaction 1, A and B react to form a desired product. Then reaction 2, A and B react to form our undesired product. Okay, that looks fine. Then we're going to loop over our tau values. Const solver. So if you look at const solver, I'm going to copy and paste this. Okay. So I'm going to copy and paste this. And if I copy and paste this, I'm just checking to make sure everything matches up first. CX, new A1. Reaction 2, that's a single tau value, which is stored as tau. Initial concentrations of A, B, D, and U, along with R and T. Okay, so that all matches up and looks good. Okay, so I unpack CX. CA, CB, CD, and CU. I'm going to rename tau T. That's fine. You also could just put T up here then. What is going on in this if statement? So if tau is less than or equal to 2, CCA is equal to that, CCB is equal to that. Else CCA is equal to 0 and CCB is equal to 0. Okay. Not sure what those mean, but let's look ahead. So we have our rate expressions. Okay. So R1 and R2. Okay. Okay, divided by RT. I noticed R was in SI units above, and that's fine, because here our activation energy is in SI units, joules per mole Kelvin. Or not joules per mole Kelvin, joules per mole. Our time now, all right, so our pre-exponential term is in units of inverse seconds, so our unit of time will be minutes in this case. Okay, mole balance design equation as we had it in the last problem. So this is tau times stoichiometric coefficient in reaction 1 times my general rate expression for reaction 1 plus stoichiometric coefficient in reaction 2 times R2. That's fine. Minus should be CA minus CA naught. Right? So I don't know what this is. Okay. Okay, and, I mean that's this quantity. So there's no reason for anything like that. Okay, so I'm just going to delete that. Okay, and then I pack up the results. Okay, but looking at this, what I'm guessing is that was introduced because this wasn't working, and that's why you sent me your code. And so this is going to come back to when we look at the initial concentrations up here. All right, so you have initial concentrations of 0 for everything. But when we look, concentration of A is 10 moles per gallon, and B is 12 moles per gallon. Okay, so A is 10 moles per gallon, B is 12 moles per gallon. Okay, so this is going to be moles per gallon. Okay, and if I look at my mole balance design equation, okay, so R, right, my rate expression is going to have units of inverse time. Okay, where here that's going to be minutes inverse. So we'll take our unit of time then to be minutes, right? So tau will take to have units of minutes, okay? So that those time units cancel as stoichiometric coefficients dimensionless. Well, and actually, I take it back, right? My rate expression has units of inverse minutes times concentration, right? So the units of time would cancel out in tau times my rate expression. Stoichiometric coefficients dimensionless, so I'm just left with units of concentration, okay, as I am here. Okay, so if we just stick with the unit of concentration being moles per gallon, right? We can just take that to be our unit of concentration. I don't need to worry about converting anything. Okay, and so that looks good and fine then. Okay, so all I did up here is I fixed those initial conditions. So we can look at range of taus, and we can plot like the last problem. We can do that. That's fine. Okay, and so then we're just passing all these parameters to our error function. And that looks fine. Those are all defined up here. And then you collect the value of A, B, D, and U. That's good and fine. And then you plot them. Okay, so I don't see anything wrong. The only thing I did is correct your initial concentrations. Okay. Oh, and let's look real quick. When you use fsolve, we have initial guesses of 0, 2, 0, 1. Okay. Let's just make this something other than. So let's make 3, 2, and I don't know, 1.5 and 1. Let's just make those something other than 0 and being the same thing. Okay. So I'm going to restore that. Okay. Plot title 1, as I peek ahead, is the input. So plot title 1. So I'm going to rename it. I'll name that plot happy. Oh, don't want to save that. All right. happy time. Okay, and so let's run it. Don't appear to have any error messages. Hey, these things run. Okay, what's going on now? My y-axis seems a little funky. Okay, let's see what's going on with my y-axis, but it's running, and there doesn't appear to be any sort of glowing issue. Okay, so you have the y limit set to be 0 to 160, so I'm going to delete that so it'll just auto scale. Hey, it looks like we've got something going on, right? Concentration of A and B declining, concentration by desired product and undesired product increasing. Okay, let's crank up the time, see if we can get some cool behavior. Okay, and if I'm going to crank up the time, I'm going to use a lint space just to prevent going crazy in terms of the number of data points that I'm using. So I'm going to use a lint space. Let's do 0, comma, that was 3. Let's try 300. Okay, and we'll just do 100 data points for now. You can always add a third argument to increase the number of data points if you want. Okay, but let's see what we have. Whoa, okay. Now, let's see, this is concentration of D. We're going well beyond D's consumed. So let's try stopping this sooner, about 100. See what's going on, and then see if we have any issues going on in our code. Okay, so if I change that to 100 and rerun, okay, what is going on? So D is actually going through an extremum, it looks like. So let me see if something, because this would say D is then being consumed. Okay, so we have everything working. Okay, let's just take a look back at the problem. All right, we have A plus B goes to D, A plus B goes to U, R1 is first order in A, R2 is first order in B. So new A1, new D, new A2, new B2. Okay, I'm just trying to look to see where that negative business is coming from, what's causing it. Okay, and see if we can make physical sense of it. DU. So tau ABDU times R1 ABDU times R2 ABDU ABDU. Let's just play with my initial conditions, just make sure I don't have anything going on. Okay, because then if I run this, what do I have going on here? I have D, so the behavior of A, all right, decreasing going to 0 seems fine. Okay, and that's my limiting reagent. All right, so it's going to be consumed to completion first. And here's my undesired species. Okay, and if I look at A, it looks like we're getting a value of A that's slightly negative. is that? And then A becoming negative, right? So the issue seems to be A, because when A becomes negative, then somehow first reactions A plus B goes to desired, all right? That's causing then negative values of D. So there seems to be possibly some sort of physical limitation of the model. That I'm having a hard time. Oh, so I believe the issue is due to this R2, right? So what's going to happen is that if A plus B goes to D, A plus B goes to U, okay? I know that A is my limiting reagent, right? Because for every mole of A that reacts, I'm going to have a mole of B that's going to react. So A is going to be consumed first, right? So if this goes to completion, I'll have 0 moles of A left and 2 moles of B, okay? Now the problem is when I still have 2 moles of B left and 0 moles of A, right? In theory, I have no more A to react. But mathematically, the challenge is R2, right? R1 will be 0, but R2 will not be 0, right? Because R2 is first order in the concentration of B. Okay, and so when I look at my mole balance design equations, here, okay, challenge is that when all of A is consumed, when Ca goes to 0, then R1 will go to 0, okay? But I'll still have some B left, so R2 is non-zero, okay? And so I think that's just an issue with the models, okay? And I swear I took this from a textbook. So if you're taking kinetics, I took it from that free online textbook, okay? But that's okay. Let's see if we can save face here, okay? And how we might be able to save face is we're looking at a specific tau value. We're looking at, so we have a 25-gallon reactor, all right? So let's see if we can calculate our tau. So, and actually, let's just do it here. So let's do 25. So we have a volume of 25 gallons. We have a flow rate of 12.5 gallons per minute. V flow is 12.5, and that's gallons per minute. So our tau value would be V divided by V flow. Okay, so 2. Okay, so now when we look at our plots, all right, we're only interested in essentially a tau of 2. All right, so let's create our plot, okay, and then let's solve for tau of interest and plot. Okay, so we have volume in gallons, so V is 25. V flow is again 12.5. It's volume in gallons and volumetric. Flow rate in gallons per minute. So V flow is 12.5. Solving for tau of interest. So let's call it tau would be V divided by V flow. Okay, and so then what I'm going to do is I'm going to copy this. So final solve will be this. So final solve would be copying this, but now we're going to use the tau of interest we just obtained. Okay, we'll solve for res. That's fine. Okay, and then what I'm going to do is I'm going to copy my plot. Doom. Okay. And I'm going to plot instead of tau, we'll have our tau of interest. Okay, and then this will be res 1. A is the first element of res. B is res 2. D is res 3. U is res 4. Okay, so you should have had to hold on and let me plot these as, say, circles. Bam. Okay, so now if I run it, so now if I run my code, okay, all right, our points of interest are way down here. All right, so they're well before we hit kind of this, physical limitation of our model. Okay, cool. Okay, and it's returning those values since I had called that last call res. So this would be the concentration of A, B, D, and U for that tau of 2. And then you could take those values and go ahead and calculate the fractional conversion and selectivity at that concentration. Okay, so again, the selectivity would just be the ratio of my desired product relative to my undesired product. And fractional conversion in my limiting reagent, which would be A, would be concentration of A going in minus concentration going out relative to the concentration of A going in. So I'd want to compute those two values and return those as well. Creating a plot like this is, awesome in terms of being able to illustrate this point. And so I guess what I probably would want to do is, say, move this material down. So then if I were to, add my print command, I would, do it down there. Okay, but yeah, so that solves it. Then you just need to take care of the rest of the arithmetic that it asked you to do in the problem. Okay, again, this is a little, oddity. A and then D taking on negative values. But the issue is that second order reaction being just first order and B, is what causes this unphysical behavior. Okay, cool. Hopefully that helps you out.